All right, in this video, I'm going to go over the solutions to our week's exercises involving capacitors and circuits. And so let me do a screen share here so we can bring up the assignment. And just in case you watch this and you don't have access to the assignment, I'll just kind of go over this really quickly, and then, well, actually, I'll just kind of I'll go through each question individually. Then, as I need to, I'll do a presentation of my whiteboard if I need to solve anything. So let's just start with number one. Number one says we have a hairdryer that is rated as 1200 watts. So when they say watts, remember watts is a unit of power. And so they're saying that it's rated as a 1200 watt power, and it has 120 volts. It wants to know its effective internal resistance. So let me bring up my board here. So what they're wondering is, we are given the power and the voltage, and we want to find the resistance somehow. And so if we remember, we have to have some way to relate all those quantities. So if we remember, we can say that the voltage is equal to the current times the resistance R, voltage, current, resistance. And we have another equation which says that power is equal to the current times the voltage. And so we don't have current. They don't tell us anything about that. But what we could do is we could solve this equation for voltage, and then, or I'm sorry, for current, and then plug that value into here for current, and we'll be left with an expression that involves only voltage and only resistance. And so for this equation, we have the current is equal to the voltage over the resistance R. And so if we plug this into here, we're left with V squared over R. And therefore our resistance then is just going to be equal to the voltage squared over the power. Let's plug those values in. Our voltage is 120 volts. We have 120 volts squared over our power of 1200 watts. All right, so what are we left with then if we plug this all into our calculator? Let's see. Okay, 120. All right, so we come up with a value of 12. So I get a value of 12. What are the units for it? Well, it's ohms. It's a resistance, so it's in ohms. Let's go back. Let's do a screen share here. All right, so if you notice the answer, then it's C, 12 ohms. All right. Number two. I'm not going to redraw the circuit on the board, but I'm going to write some of these numbers down. So take a moment as I write this on my board to review this problem. But essentially, we have a circuit with two different resistors that are in parallel with each other. And then we have an EMF due to the battery. And the question is what is the internal resistance of that battery given the current through the circuit? And so I'll switch screens in just a second, but I'm going to write down some important stuff. So I'm going to write down the EMF is equal to 20 volts. I will write down that the current is equal to 0.8 amps. The resistance, well, I'll have to figure that out, and then I also have to figure out the resistance of the internal resistance. All right, so let me stop my screen share here. Okay, so the first thing I have to do is I have to find the resistance of that circuit. Well, I have two resistors that are in parallel, and so whenever we're dealing with a circuit like that with resistors in parallel, we can find the equivalent resistance of that parallel part. And then if we rewrite that parallel part with that equivalent resistance is now in series with the rest of the circuit. And so I'm going to go ahead and do that. How do I find the equivalent resistance of resistors that are in parallel? Well, we have that formula which says the equivalent resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus however many resistors you have. We only have 2, so I'll end it here. And then we take the inverse of all that. And so therefore, when I plug it in, I have 1 over 30 plus 1 over 60. I'm taking the inverse. All right, so I should get an equivalent resistance of 20 ohms when I do my math there. All right, so my resistance then is 20 ohms. All right, So how do I find the internal resistance then? Well, we have to relate that to the EMF in some way. And we have an equation. And I will say this, is that I think when it comes to circuits is understanding what EMF is and how you can use that with Kirchhoff's loop and junction rule are probably the hardest part about circuits, for me anyways. And so if you need help with that, I can give you some references to look at. But the important point, the basic equation that we'll use says is that the EMF is equal to the current through the circuit times the total resistance of the circuit and the battery. So that'd be R plus little r. You'll also see this written like this. You'll also see it written as IR plus I little r. But think about what IR is. That's the voltage. So we're talking about two different voltages here. What voltages are they? Well, think of this as the voltage that you would lose. What do I mean by that? I mean that if a battery has internal resistance, so let's say you have a battery that has an EMF of 1.5 volts, but when you connect it to its circuit, because there's an internal resistance to that battery, you're not going to quite, and then if you put some terminals on that battery, you're not going to get quite the exact same voltage as your EMF. It's going to be a little bit less due to that resistance in the circuit or in the battery. And so therefore we call that amount that you lose, we could say it's the voltage lost. And so you could say that IR would be the terminal voltage plus the voltage that is lost. That's the way I like to write it. Another way of writing it is just saying that it's the voltage across the resistors or across the circuit plus the voltage across the battery. Oh, that should be a little r. All right. So that said, we're looking to solve little r. So let me erase this here. We're looking to solve for little r. We have all the other variables that we need. And so therefore, if we plug it in, we have 20 volts is equal to 0.8 amps times R of 20 plus little r. What do we get when we multiply this out? Well, 0.8 times 20, that's 16. That's 16 plus 0.8 r. I'll bring the 16 over to the other side, and that leaves me with 4 is equal to 0.8 r. And so therefore my internal resistance should be 5 ohms. All right, so let's go back and let's take a look at our options, see if that fits one of them, hopefully. And it does, so it's C again. So we have an internal resistance of 5 ohms. All right, number 3 says we have an EMF of a battery is 12 volts. When the battery delivers a current of 0.5 amps to a load, the potential difference between the terminals of the battery is 10 volts. The internal resistance of the battery is. Okay, so this is really asking something very similar. So it says that our EMF is now 12 volts. We have a current of 0.5 amps. And, okay, oh, I see. Okay, so it gives us it gives it to us in a little bit of a different way, but let's see what we can do with it. All right, so our EMF is equal to our terminal voltage plus I times little r. Again, it wants to know the internal resistance of the battery, so let's just plug in the values that we have. And oh, sorry, I forgot to do my screen share here. In fact, here we go. Let me bring it up so I can see. Okay, so we have 12 volts. We have a terminal voltage of 10 volts plus a current of 0.5 times R, so it's 0.5 times R. So bring the 10 over to the other side, so we have 2 is equal to 0.5 R. What's 0.5, or 2 divided by 0.5? That should be equal to 4. So we have an internal resistance then of 4 ohms. And if I go back, Okay. If I do my screen share here, let's see if I have an answer of 4 ohms. Okay, so again, it's C then. The answer is 4 ohms. All right, number 4 says the total equivalent resistance between points X and Y in the circuit shown on the left is. So it wants to know essentially how do you get the equivalent resistance of 2 resistors that are in parallel with each other and then they're in series with one other one. And so, all right, so let me write this on my board. All right, so we have a 2 ohm resistor. So we're going to say 2 ohms is the output R for series, and then R in parallel, RP for R in parallel, and that's equal to 1 over 2 plus 1 over 2, all inversed. So let me stop this screen share here. Okay, and so, well, if we're adding a half and a half, that's equal to 1. The inverse of 1 is still 1. And so our equivalent resistance of those two is just 1 ohm. And since that's in series with the 2 ohm resistor, we just take this and add it to the one that's in series. And so therefore our total resistance is going to be equal to 3 ohms. So our total resistance should be 3 ohms. Let's go back one more time. Okay, so then for 4, the answer would be A, so it's 3 ohms. All right, let's see if we can get through one more. So number 5 is all about resistance. We have 5 different resistors shown below. They have lengths and cross-sectional areas indicated are made of materials with the same resistivity. Which resistor has the least resistance? All right, so let me stop screen share here. And then let me bring up the problem myself so I can look at it. All right, so what is the formula? What tells us what the resistance is given the resistivity? Well, again, electricity lends itself well to analogies with water, and so, or water or air. And so if you think of a resistor as a straw, how difficult is it to blow through that straw? Well, the longer the straw is, the more difficult it is. But the wider it is, the greater the area of the straw, the easier it is. So as the length increases, the resistance increases, and as the area increases, the resistance decreases. We can write that mathematically as we can say that R is proportional to the length over the area. But I think there's a little more to it, because if that's true, every material of the same dimension would have the same resistance. We know that's not true, so there's some proportionality that we need to put in there. We call that proportionality the resistivity. It just tells us about the material itself. For instance, copper. Copper has a really low resistivity because it's so good at conducting electricity. It has very little resistance. And so we could rewrite this equation in the exact form as R is equal to rho. This is a rho, it's called the resistivity. It's unique to whatever object or material it is, times the length over the area A. Okay, and so now we need to look at the different options and see what we have. Well, let's see here. Okay, I'm kind of running out of time here, so I'm actually going to stop this, and then I'll pick back up in just a second on my next video with it. But take a look at problem number 5, and given this equation right here, and see which one is going to have the least resistivity, which one will have the greatest, and then everything in between. So I will be right back with my next video.